Good day, welcome back. In the previous video, we talked about the Lagrangian mechanics and the requirements of writing Lagrange equations for rigid bodies. So it was more of a general description of what we need. So let's look at just one quick example how the Lagrangian equations might look like for a single rigid body. There is no unique way to do this. We'll just use one example approach, but hopefully it shows the process what we can expect from Lagrangian mechanics in rigid bodies. So to start, I don't want to write it down. Let's consider a rigid body. So I have my inertial frame, a rigid body in this frame with some center of mass. So what I can do is attach my body fixed frame to the center of mass. So this point is center of mass, COL. If I do that, I can write the, I can write my kinetic energy, T. We had seen it before. It's the translational kinetic energy plus the rotational kinetic energy. And this one is 1/2 m x dot squares. So this is, if this is x, this is y, this is z, all of them capital. They are my inertial frame. And this one is y, this one is x, that one is z. So x dot squared plus y dot squared plus z dot squared plus 1/2. Let me write the matrix notation again. Omega transpose times I times omega. So here, and maybe there is gravity, maybe not. We don't care about that for now. So if you want to write Lagrangian is kinetic energy plus potential energy. Let me write it down, potential energy too. And let's pretend there's gravity this way. And V equals mgy, the height of the center of mass. So Lagrangian is T minus V. What I want you to note here is that when we want to write the Lagrange equation, it's I have partial L partial Q dot and partial L partial Q. So if I take the positions of my, so take Q's to be the XY, and Z, the rotational ones, and some, what did I say? Translational, these are translational ones, and some rotational variables. Let's use this notation, psi, theta, phi. See, so if I take 3 translation and 3 rotation as my generalized coordinates, this one, the translational part of kinetic energy, is only a function of translational variables, and the rotational part is only a function of rotational variables. So only f of translational vars, and this one is only a function of rotational variables. So when I take the derivative of this t with respect to my q dots, essentially I separate the equations. All the translational equations only involve translational variables, and all the rotational equations only involve rotational variables. So in some sense, with this choice of variables, I have decoupled the translational and rotational equations of motion. So this choice decouples the translational and rotational equations of motion, which simplifies life in general a lot. So translational is easy. If you look at the kinetic energy, for instance, you take the derivative with respect to, I don't know, x dot, that would be mx dot, and then take time derivative of that, mx double dot equals forces, generalized forces. So easy equation. Let's for now focus on the rotational part of Lagrangian mechanics. And for simplicity, consider the little xyz frame, xyz, the body fixed one. I didn't write it well. XYZ frame to consider to be my principal axis, just for simplicity axes. And I don't have any product of inertia, only moments of inertia along the diagonal of the inertial matrix. So in that case, my T, or the rotational part, T rotational is 1/2 Ixx omega x squared plus 1/2 Iyy omega dot squared plus 1/2 Izz omega dot z squared. This was y. So this is my kinetic energy. The problem is this. Why did I write omega dot? Omega. This is z. So the problem is that these omegas are not some q dots where the q is my generalized coordinate. So in other words, these angular velocities, omega I, is not something I can write as q dot I. I need to figure out something. Q's are the generalized coordinates that describe the orientation of my body, and a good choice for that are Euler angles. Euler angles are very easy to interpret, easy to measure in real systems, and very useful variables to consider when we are describing the orientation. So I can use Euler angles, and let me use as an example zy, well, not zyx, z little y, this one. What am I doing? Zyx sequence with variables psi, theta, and phi in that order. These are my generalized coordinates. Generalized coordinates. These are my QIs. QI is the 3 rotational ones. So the only thing I need to do is write the kinetic energy in terms of derivatives of these Q dots. And we have already looked into that. So remember, recall that when we were talking about angular velocities and in relation to Euler angles, I had omega x equals phi dot minus psi dot. This is psi dot sine of theta omega y equals psi dot cosine of theta sine of phi theta dot cosine of phi, and omega z equals psi dot cosine of theta cosine of phi minus theta dot sine of phi. So we had seen these before, and for different Euler sequences, I don't know, z, y, z, these relationships would be different, but you can always find them. And now if I plug these omegas into the definition of my t, I can write my t rotational as a function of psi dot, well, essentially as a function of my q dot I and qi. I can write it this way and use that in Euler equation. For instance, equation of motion for psi, the first one is d over dt of partial L partial psi dot minus partial L partial psi equals Q or Q sub psi. And well, because of this situation that I have up here, there is no the potential energy does not depend on any of these orientations because I have chosen the reference point of the frame to be at center of mass. So as the body rotates and changes orientation, the potential energy doesn't change. So in this case, let me write it L rotational equals T rotational minus V rotational equals just T rotational. Yeah. So you can take the derivative with respect to psi dot and then time derivative of that minus derivative of L with respect to psi equals your generalized force, and that is your equation of motion. So I'm not going to write it down. It is going to be a gigantic equation. You will have 3 of these, same for theta and phi. You can write the equations for those generalized coordinates as well. If you do that, you get 3 second order coupled differential equations, or ODEs, ordinary differential equations, in psi double dot, theta double dot, and phi double dot. Those equations will be huge. They are written in the textbook, so you can look at them. But they give you very they can give you equation of motion described in three rotational variables, psi, theta, and phi. So it is possible to do it, to write equation of motion for, let me write a bit better. Equation of motion for rigid bodies. You have three translational ones that are easier and three rotational ones that are gigantic. All right, so the only thing I want to mention here, and we can expand on it in the next video, are these generalized forces, Qs. So if I go here, if I have some forces and moments, let's bring all the forces to the center of mass and add whatever leftover moment they may have, or add other external moments. At the end of the day, there is going to be some vector of m, the external moment acting on the system. To find these Q's, generalized forces, associated with each of these variables or generalized coordinates, we can go back and refresh our memories. We use the concept of virtual work, and we're going to do the same thing. So virtual work, delta W, is the amount of work done by these external forces and moments given an infinitesimal virtual displacement. And virtual displacement was similar to actual displacement, only the difference was time is appeared to be fixed or frozen. So in that case, so I can have my vector of external moments dot some small, if I very tiny wiggle my psi, this is one part of the virtual work. I can do the same. I have m and I wiggle around a tiny bit, delta theta, and lastly I can wiggle around a little, delta phi. And these are vectors. Remember that for infinitesimal rotations, we can define these rotations as a vector, define the direction of the axis of rotation plus, and the magnitude is the size of rotation. You can do that. And this is the total virtual work. If I move my body just a little, change the orientation a little, that would be the virtual work of the external moment m. And I can write it as m dot. So this delta psi, the vector, is some vector with the magnitude delta psi along the direction of my axis of rotation, which in this case is Ez. Plus, I can do the same thing, m dot delta theta, the scalar value, times the unit vector Ey prime. That's the second axis of rotation, plus m dot delta phi Ex double prime, my third x axis of rotation, about the latest x. Just a change of order. It's going to be m dot Ez delta psi plus m dot Ey prime delta theta plus m dot Ex double prime delta phi Oh, what did I write? Delta phi. And this is in the form of sum of Q times delta Q. So this is my Q psi. This is my Q theta, and this one is Q phi. So if I have these external moments, essentially the generalized force associated with that particular direction is the net external moment along that direction. So that is m dot these unit vectors. And yeah, I don't think I have anything else. So we didn't do anything special or fancy other than writing same old Lagrange equation that we had using these rotational generalized coordinates. So that's it. In the next video, we will look a little more into generalized forces and introduce a concept called angular velocity coefficients, which is kind of useful for system of rigid bodies. All right, until then.